Starting off the last afternoon of this conference already went very quickly. So it's my pleasure to introduce Sebastien Bossu from University of North Carolina, also an invited speaker. Happy to have you. And he's talking about spanning multi-asset payoff with ReLUs.
Well, thank you very much for the invitation. Very nice to be here. And maybe a fair disclaimer is that this is more of an analysis talk than probability talk, but probability is analysis, so there is connection to be found. The reason for that is because I'm focusing on payoffs, so this is a model-free type of analysis. And so I'm having a distributional and neural network approach. This distribution is Schwartz distribution as opposed to probability distributions. Joint work with Stéphane Crépet and his PhD student Hong Dong Nguyen at University Paris-Cité. And let me get started here. So I talk about multi-asset payoffs, and I come from industry, so I saw a number of these payoffs trade. And so the sort of from most liquid to least liquid, you have a basket call or put that could be written as the dot product of basket weights and X being a price vector or price ratio from final price to initial price minus some constant strike K positive part, and that's for a call. For a put in this reverse. I'll talk after about the absolute homogeneous variation. And then commonly found in industry are best of call and put. So it's a call on the highest of, let's say, Apple, Microsoft, IBM price at the end, minus a strike positive part, and you have a put version as well. Worst off is a call on the worst price. You have also binary versions where you get $1 if the worst of the best stock is above a strike, or if the worst stock is above the strike for the worst off binary. And then one of least liquid, but that still trades is the dispersion call or put, which is going to be a sum of absolute values of returns, really, in this case, and so that trades, with high strength. One of the sophisticated. So it's an L1 norm, a call on the L1 norm. Absolute homogeneous variation is really relevant for the second part, and that's just putting absolute values everywhere, so that if we multiply X by lambda and K by lambda, we get the absolute value of lambda times the original payoff, and that's relevant for technical reasons. Okay, so dispersion call, I will skip there quickly, but this is an example of a term sheet of a transaction between a bank and a customer, and so you see as the payoff, you have something that is the positive part minus the strike of the dispersion, and dispersion is the sum, let's say equal weights of absolute values of returns ish. Okay, so I'll start with the easier part, which is section 5 of that paper on archive, which is the really connection with machine learning, and then go on into depending on how much time also we have on the distribution part. So I have a target payoff, just as like one of the ones that I listed. And we have target payoff f of x, and we're trying to decompose that with basket calls. The reason being that basket calls are easier to price and source, and so this is very interesting to industry. And so we try to find quantities nu I of some basket call number I, where the weights are specified by this W vector, Wi vector. And we also allow for some constant cash and combination of the underlying assets. And there's an error term, and we're trying to minimize the error. So this is a nonlinear regression type of setup. And mathematically, so we want to find the optimal parameters so that we minimize the error according to some error metric. That's going to be, for our case, MSE, mean squared error. And so we try to minimize the norm across a sample of X values of underlying asset price values, and so yeah, we minimize the distance between the target payoff and that replicating portfolio or at least approximately, or hedging portfolio, or spanning portfolio, as we call it. Okay, and so this actually has a very nice neural network interpretation, because it can be solved numerically by training a single hidden layer neural network with ReLU activation function. So the ReLU activation function is essentially a basket call in finance, so really nice connection. And so we try to reproduce that target payoff, or predict, I guess would be the correct term, target payoff using these ReLU, a bunch of ReLUs. So these are kind of standard notations here. And for that, we use the Adam stochastic gradient optimizer to get numerical results. So numerical results, produces some pretty graphs. So the target payoff is that surface, the blue surface, and then the dots are for a random set of vectors x1, x2, or sorry, prices x1, x2, or returns x1, x2. And so you can see how the dots are pretty closely aligned with the surface that we're trying to predict or replicate. And then there are some contour plots. So the true payoff that we have in the case of the best of call would be a picture like this. The prediction is pretty close, not perfect, of course, there's some residual error. And then the absolute error, very interestingly, is pretty good on the flat portions of the payoff, but actually there is some substantial error that sometimes can happen at the edges where the payoff is non-differentiable. And we have, our example. This is for the dispersion call, and we get, again, pretty good visual replication of that with some errors, sometimes substantial, again, in the areas where there is no differentiation, so around the edges. But one of the best results with lowest error is a very smooth payoff, and so we get, I call this Mexican hat. So that doesn't trade, but essentially, we get very close replication with the basket calls of that payoff. So I'll probably just, in the interest of time, go a little quickly here, but we have this optimization through learning, and so that we could call this as a unconstrained hedging strategy, and again it's static hedging or spanning as we call it. And we benchmark that against other types of strategies that are especially interesting for industry. So, industry likes hedging with just single asset calls and puts, because these can be sourced from even listed markets. And so, in this case, we have a highly nonlinear payoff in all the dimensions, and we try to hedge this with just vanilla calls and puts on a single asset. And of course, we can change the asset and let the optimizer choose what's the best hedge here. We also had, a case which is essentially a linear regression. We fix the basket weights and also the strikes of the basket calls. And then we find the optimal quantities of these basket calls and puts. And so this is, no longer nonlinear. It's a linear least square regression. And also, another strategy is having only basket calls and puts where the basket weights are long only, so positive basket weights. Okay, and so we got essentially, the unconstrained optimization gives the best results, and you can quantify this. Some of the usually worst results is if we try to hedge only with single asset calls and puts. And surprisingly, that gives you, higher error. And the unconstrained NN, which is the violet here, is typically consistently gets you better results. So sometimes there are certain strategies that are a little bit better in some cases. So this for every possible payoff that we discussed in that paper, including the dispersion call, worst of binary call, things like that. And this is for 5 assets. That's our dimension D, 78 options. And then running that for several network analyzations. And then this is for higher dimension, 50 assets and 800 basket calls and puts. And so we got also very good results. So that's for the sort of feel good, kind of very hands-on part. And we looked into the more mathematically interesting and challenging problem of continuum spanning. So yes. So the loss function is going to be, depending on how you look at the loss, the distance between your target payoff, let's say your basket call, sorry, your best of call, and then you're replicating that or hedging that. Well, that would be a mean squared error, although this is open to definition. Yeah, yeah. So this is like a least square type of, optimization. Yes. No, so yeah, we could say Lebesgue measure. I mean, this is kind of statistical. We have actually big N values of samplings of a vector of prices. So we do a grid, or we could do, depending, if we have small number of assets, we do a grid. And if we have a high number of assets, we'll do a random sampling. No, so the optimizer will optimize, the W's, just like a neural network kind of setup, right? And the biases are also optimized. Yeah, arbitrarily many, yes, in the unconstrained neural network strategy, yes. And the later slide, that's the number, okay, the 800, the n equal 800 is the number of basketball options. So we allow a number of neurons, if you want. Oh, that is pre-specified, yes, yeah. It's a finite dimensional, yes, absolutely, yeah. Thanks for, yes. The baskets, yeah.
No, like how much you can invest.
Oh, no. So this is, no constraint in money, because this is not an investment strategy. This is a replication. So we look at the payoff. And so it's for 1 unit of derivative. And then we have quantities. And there is no restriction on the quantities of the basket calls and so on. So we don't look at it. This is very simple, kind of, just to also make the problem very concrete. So essentially, we're trying, just like, a bank, we have a complicated payoff. And we are trying to kind of, replicate it with, basket calls that are easier to source and price. And then, especially interesting for pricing of a complicated payoff and so on. But there is a residual error. We try to minimize the residual error. We do a least square error, but, it's open for other types of errors. And we report the results with absolute error rather than squared error, because that's more intuitive for practitioners to look at the absolute error between, it's a dollar error of your payoff versus what, the portfolio you're trying to replicate with. Yeah. So it's with a small number of options, 800 options when we have 50 underlying assets. In the previous slide, we had 5 assets. Oh, yeah, so this is European, so it's a fixed maturity. We're not looking at anything intertemporal. It's a one period kind of situation. Thank you, yes. Oh, yes. So these would be fixed quantities of the assets. Mu is going to be, mu1 is going to be the quantity of Apple, and then mu2 is going to be the quantity of, yeah. So because we allow for cash and assets in addition to, so linear terms in addition to nonlinear neurons. Yes. Yeah, thank you. All very good questions. So yeah, I'm just trying to rush a little bit, but we have 50 minutes for. Okay, so the rest is the continuum spanning problem. And so, the reason we call this spanning is in honor of Carl and Madan's spanning formula, very relevant for practitioners. When I was in industry, this was really, a very powerful result, which is that, any single asset payoff, so now we have not a vector X, but a single variable X, can be decomposed as a sum of cash and forward contract, X minus, some constant. And then, a bunch of calls and puts in quantities F, the second derivative of a payoff, that is there. So it's a straightforward consequences of Taylor's theorem with remainder integral form. Very famous application of our log contract. You can decompose the log contract as with cash forward contract, and then calls and puts in quantity, continuum of calls and puts in quantity 1 over k squared, which is the second derivative of the log. Okay, and this had, gave all kinds of applications for VIX, variance swaps, and things like that. And so there is a neural network interpretation, which is that any twice differentiable target function can be predicted attained by an infinite width one-headed layer ReLU network. So a idealization of the finite ReLU networks that people deal with. And so there is a ReLU machine learning literature, no connection with finance, where we found actually the Karan-Madan formula in slightly different form, but essentially equivalent form. So independently, I guess the machine learning literature also discovered the Karan-Madan, and all this goes back to Taylor's theorem anyway. And in my thesis, I looked into the more ambitious problem of multi-dimensional, so multi-asset spanning. And in this case, we have now a vector of prices for your payoff F that you're trying to predict or replicate. And then there are first order terms, the cash and underlying assets, plus we have a multiple integral. And then we try to find quantities nu of W of all the basket calls you can think of. And so we integrate over all possible basket weights W. So this is actually an integral equation. We try to find the function nu of the basket weights. And so I showed that essentially the that solution is the inverse radon transform of the second derivative with respect to strike, which is close to the in Karan-Madan, we don't have a radon transform inverse, but we have a second derivative of the payoff. So there is a connection. Okay, and so especially like works very well for smooth payoffs. So the Mexican hat, that doesn't trade, but is nice mathematically, can be replicated with these basket calls in quantity nu. That there's even a closed form solution that involves Dawson F function. So anyway, all that is in closed form. It's even easier in dimension free, but I didn't want to copy that. And so, financial interpretation is that any absolutely homogeneous multi-asset European payoff can be replicated by a combination of cash for contracts and a continuum of vanilla basket calls. So this is the closest we can get to Karan-Madan, which is just using calls and puts. And your network interpretation is that, well, any function you're trying to predict can be attained by an infinite with one hidden layer ReLU network. So kind of universal approximation theorem. But we even have like a solution. If you think about nu as the quantity of the neurons, or the weights of the neurons, then we have a closed form solution. So you can calculate the infinite with neural network solution using that inverse radon transform too. Okay, and so one of the issues is that, well, but in finance, we deal with a lot of non-smooth target functions. And so even in dimension one, if you try to use Karan-Madan on a straddle, which obviously is a call and a put, so you think it's pretty easy, but in order to do that, well, yes, you can apply the Karan-Madan formula and say, well, we take the second derivative of the payoff, but then you have to use a generalized derivative, and essentially a distributional derivative, which is that the second derivative of a straddle is going to be a Dirac delta function that is infinite at 0.1 and 0 otherwise. And so it's not a real function. So essentially, this is an invitation to look into the Schwarz-Sobolev theory of distributions, which I knew not much about, before all this, and it's very fascinating, but sometimes a little heavy. A best-of call, I found a spanning formula in my thesis, but there were some details left for later research, and I guess this is kind of an answer to that. So I got a closed form solution in the quantities of basket calls that would replicate a best-of call option, but the thing is that if you try to put that into a double integral against the weights, you have an integral that doesn't converge and has to be regularized, and so that was left for later research. And then the other interesting non-smooth target function is the dispersion call, which is what we focused also in this paper. Okay, so for that, it's an invitation to generalize this problem, the spanning problem, using a weak formulation, a distributional formulation of that problem. So there is some sort of standard tools and concepts, from the theory of Schwarz distributions. So the idea is that we are going to essentially modify, we have these non-differentiable payoffs or maybe non-integrable payoffs or functions in general. And so we're going to modify them by multiplying them and integrating them against nice functions that are completely differentiable and smooth. And so one type of such functions, which are called test functions, is infinitely differentiable test functions with compact support. And another type that is a little bit less restrictive is the so-called Schwarz functions that are infinitely differentiable, and also rapidly decaying functions. So, they still go to infinity, they cover a real line, but they vanish faster than any inverse power of z, any polynomial of the norm of z, as the norm of z goes to infinity. And that also has to apply for any of the partial derivatives of that test function. And then there's sort of standard notation now in that theory of distribution, which is that, some distribution t, and I'll give some examples. That has an action on phi. Phi is one of these modifier Schwartz functions, for example. And so you can just think of that bracket notation as an integral of t and phi. So very easy kind of distribution is a function and measure type distribution. Let's say measure type nu of dz. And then that bracket notation is going to be the integral against of phi against the measure nu. And so this is kind of familiar. You also have other types of distributions, the Cauchy principal value, which often notation here is an integral with a bar. And so this integral doesn't converge, there is divergence at point C. Z here is real number, by the way. But anyway, so you take you remove that singularity and you take an epsilon around the singularity, and then you take epsilon goes to 0, and you take that limit, and that's the Cauchy principal value distribution. I'll skip that slide because it's technical, but I'll get back to it just in a moment. The assumption that we have is less restrictive than twice differentiability. We say that the target payoff function has to be continuous, at least in the price vector x, and also in the parameter, the strike parameter k, and such that when modified by a rapidly decaying Schwartz function, this is integrable in x and k. And then the problem, the weak formulation of a spanning problem becomes this equation, where on the left-hand side we have our modified payoff with some modifier phi 0, which is slightly different than, but more or less you can think about it as a Schwartz function, rapidly decaying Schwartz function, so that converges thanks to the assumption. And then we have modified basket calls, that's the inner integral here. And then the quantities of the basket calls are going to be a distribution n. And so that bracket here in the most general form is general action of that distribution n on modified basket calls. And n is a linear form on an appropriate function space. So that's the formulation of the problem. So it looks a little different than what we have, but I show after that it coincides with a strong formulation of the spanning problem. And it's equivalent also to another way of writing it, which is finding a linear form on proper Schwartz functions, that are even. So sometimes you will see n, sometimes you'll see t for convenience reasons. Let me just go back so you can see some new notations that are appearing. But the space of the test functions or modifiers is called S0 here. And so let me go back to the previous slide. So S0 is really the product of a rapidly decaying function h of x, Schwartz function in x, but also with this kind of unit imaginary circle in k. And so we have a sort of dual action here, which is we modify in x, but we also switch to Fourier space in k. So I won't go through unless there are people who really want to follow every notation, but there's a lot of technicalities I'm just going through. And one of the reasons we also look at t. T is formulated with n, but t would be a sort of classical distribution, a Schwartz distribution, so-called tempered distribution that acts on Schwartz function. And so if in the most general form, we just look for a linear form. To have a Schwartz distribution, we also need to have continuity. And in some cases we do, some cases we have a more general solution. Okay, and so one of the, I think, interesting things that we did in this paper is also recovering strong solution from weak solutions. So, this is here the equation of the equation we're looking for. We're trying to find a solution n such that the left-hand side matches the right-hand side, right? And if it turns out that our solution is of measure type with finite second moment, then we recover a pointwise spanning formula, meaning that the payoff pointwise is going to be replicated by, a continuum of basket calls with quantities defined by, the measure mu corresponding to the solution. Okay, and I will skip the sketch of proof here because there is enough time left. But essentially, if the solution tends to be a nice measure type function, then we coincide with a strong spanning, and we got some identities here. If it's not measure type, then the integration over k and the action of n do not commute necessarily, and so we cannot do that. But we have a regularized expression where we can have pointwise payoff. But then it gets a little bit harder, but we do use some Fourier transforms and so on in order to get a some kind of regularized expression for the decomposition of f into basket calls inputs. So here is our main theorem. So we show that this formulation of a spanning problem, it's not the only possible formulation, but with this particular formulation, it has a solution n, being a distribution or linear form, or equivalently t, if and only if the target payoff function is essentially absolutely homogeneous, which is that if you multiply x and k by a constant lambda, you recover the payoff multiplied by the absolute value of lambda. Okay, it also has to be even in x and k, and so that's the theorem. And on top of that, we do have actually a solution, a formula to calculate the solution based on Fourier transform type of, so we have an explicit formula to calculate the solution. And, I'll just skip there. But one thing is that, if we have a temperate distribution, then, TF is a distribution. And then also, there's a connection with those radon transforms that I mentioned earlier. So we show that if the payoff f is also twice differentiable and there's some additional regularity conditions, then the solution can be shown to coincide with the inverse radon transform, just like I found in my thesis. Okay, so here's some explicit examples. So the easier examples tend to be the smooth payoff function, which typically don't trade. But at least for mathematical satisfaction, it's we get these kind of post-form solutions. So this is the payoff where it's the norm of x exponential of minus the strike square divided by the norm of x square, and it's continuous. Integrable against a Schwarz function after multiplication by a Schwarz function. It's absolutely homogeneous. It's L1, infinitely differentiable, all that. So the solution to the weak spanning problem can be calculated explicitly. And so, for example, in dimension 2, I get this kind of quantity nu, if you want, of the basket calls. And so we recover a strong spanning formula, which is that the payoff can be decomposed as sum of basket calls times we call it f here instead of nu, but it's the same idea. It's the quantity of basket calls. So it's a kind of nice non-trivial identity, which we made more explicit here in dimension 2. Now, the really interesting thing, really challenging, is to go for a payoff that actually trades here, which is the dispersion call, which is a call on the L1 norm of the vector of terminal prices minus the absolute value of k, positive part. And so we got some solutions after calculations. These are what these solutions look like. So we have some Cauchy principal value. I will probably skip because these are maybe a little bit long formulas, but not that complicated in themselves. But I will just, that's the general formula. It gets a little bit, harder in notation. But, to see what kind of spanning formula we have, decomposition of dispersion call in dimension 2. So the payoff is, the sum of absolute values of the returns or prices minus the absolute value of k, positive part. And so we get this, little convoluted expression, but still, fits in a quarter page, which is that, we get, so let's see, here we get modified basket calls. Hn here is a delta sequence, so you can think about it as, delta, 2 minutes left. And then, we have some Fourier transform, and then we have some Cauchy integrals, which, are actually iterated Cauchy integrals. And so, after all calculations, essentially, this is shown to correspond to that payoff. So, the thing that, we're still thinking that it might be possible to get rid of these Fourier transform expressions here. But otherwise, you get something that is as close as you can as essentially a portfolio, a continuum of basket calls with Cauchy integrals here. So that's the result we got. And yeah, I have some conclusions and references. So finding those static hedges are very interesting for industry. And so we found some continuum replication for industry dispersion call, and we have also regularized solutions. And then the discrete spanning, which gets really, I presented this in the Quant Minds conference in London last year. I had a lot of questions from industry. Of course, the industry is also very interested in the more hands-on, finite spanning, discrete spanning. But then you have still a replication error. You try to minimize the error, but you still have an error. Whereas, of course, in the continuum case, you have zero error. You have a perfect replication. And just one last word is that I think the slides will be probably published. So there's an appendix, and if you know nothing, like I did in period distribution, then there are some appendix slides about giving some examples, hands-on, so gentle introduction to the theory of Schwartz distribution. So with that, I got finished here. Do we have time for? Thank you.